Hello everyone, my name is Nuanjula Samarasinghe. Today's lab is capacitance. So before we talk about capacitance, let's talk about capacitors. So have you ever seen this one before? So here's the capacitor. So what is a capacitor? A capacitor is a device that stores electric charge. And what's inside capacitor? So here you can see this is the inside of a capacitor. And mainly it has two plates separated by a fixed distance by air, vacuum or some kind of insulators. So we know that the capacitor can store electric charge. So then the question is, how much charge can a given capacitor hold? The amount of charge capital Q a capacitor can store depends on two major factors. The one is voltage applied between these two plates, and the other one is capacitor's physical characteristic, such as the area of the plate and the distance between plates. So now let's talk about the capacitance. A given capacitor's ability to store charge at a given voltage is called its capacitance. In other words, the capacitance is the ability of an object to store electric charge. So that means the capacitance, we can define the capacitance capital C. The capacitance is the ratio of the change in electric charge of a system to the corresponding change in its electric potential. So capacitance C is equal Q divided by V. And the capacitance of a capacitor is measured in farad. So that is the unit of a capacitance, it's capital F. And Q, it's the charge, it's measured in coulombs, capital C. And this is the voltage across a capacitor and it's measured in volts, capital V. So here's the capacitance, C equal Q divided by V. So let's talk about the capacitance of parallel plate capacitor. The parallel plate capacitor has two identical conducting plates. So here you can see it, and each having a surface area capital A and separated by a distance simple d. So here's the simple d. And in this case, we assume we don't have any material in between these two plates. It's just air or free space. So then how we can define capacitance for this parallel plate capacitor? So the capacitance of this parallel plate capacitor C depends on the surface area capital A and the separation between these two plates simple d. So capital C is equal A times epsilon 0 divided by simple d. So epsilon 0 is the electric permittivity of vacuum and it's this value. And the main thing is this equation is valid only when the parallel plates are separated by air or free space. If we have any kind of material, any dielectric material between these two plates, then we have to modify this equation. But today I'm not going to do that. So then the another important thing is, how do you store more charge? How we can increase capital Q? So we know capital Q is equal to capacitance times voltage, C times V. So if you want to increase Q, what we should do? So think about capital C. If you increase capital C, the capital Q will also increase because they are directly proportional. And now we know capacitance capital C is equal this equation A epsilon 0 divided by D. So what I need to do, I need to increase capital C. So if you want to increase capital C, what we can do, we have two options. So the one is capital A. If you increase capital A, C will increase because they are directly proportional. And the other way is simple D. If you decrease simple d, then C will increase because C and D are inversely proportional. So that means we can do two things. We can increase capital A, then capacitance will increase, or we can decrease simple d, then again capacitance will increase. So capacitance will increase mean capital Q will also increase. So that's the way we can increase capital Q. We can store more charges. So now the next question is, what is the electric field between these two conducting plates? So here you can see we have electric field, and the direction of this electric field is going from positive plate to negative plate. And now I'm going to find the electric field between these two plates. So before I go to that part, so if you remember lab number 4 Gauss's law, we talked about the electric field near a large sheet of charge. So here's the large sheet of charge, and we found the electric field near this large sheet of charge. It is equal to charge density divided by 2 times epsilon 0. So we used Gauss's law, and then we found the electric field capital E near a large sheet of charge. But today I'm going to find the electric field near a conducting plate. So basically we have to follow the same steps, but let me show you how to do that. So here you can see this is the section of infinite conducting plate, and then here's the cylindrical shape Gaussian surface. So in this Gaussian surface we can find three surfaces. The one is this one. So here you can see this is the area vector, and here's the electric field. And then the second surface is this surface, and here's the area vector, it's this way, and the electric field here is 0. Why it is 0? So this electric field means the electric field inside this conductor. So electric field inside a conductor is equal to 0, and I will show you why it is equal to 0 in next slide. But now you can see it's 0, and here's the first surface, here's the second surface, and the third surface is the side one, and here's the area vector for that third surface, and here's the electric field. So now, so these are the three surfaces in this Gaussian surface. So now let's try to write the equation for the charge density. A conducting plate has a charge density sigma. So we know charge density is equal to Q enclosed, the charge divided by area. So that's the charge density. And then we can solve this equation for Q enclosed. So Q enclosed is equal to sigma times A. So we found the total charge enclosed by this surface, which is equal to sigma times A. So then now let's try to find the net electric flux passing through the surface. What is the net electric flux passing through this Gaussian surface? So we know the flux is equal E dot A, the dot product between electric field and the area vector. So the dot product mean it's a cosine, so we can rewrite this equation as E times A times cosine theta. So now basically we have to consider like three surfaces. So the first surface, it's E times A times cosine 0, because the angle between electric field and the area vector in this case for this surface is equal to 0, because they are going in the same direction. So therefore the product E dot A for this surface is E times A times cosine 0, which is this part. And the second surface is this one. So now I'm going to find the same product E dot A, but here you can see the electric field is 0, therefore the product E dot A is equal to 0. So this surface will not contribute to the flux. So that's the second surface. And the third surface, you can see the electric field and area vector. These two are perpendicular to each other. So that means the angle between these two is equal to 90 degrees. So then E times A times cosine 90. We know cosine 90 is equal to 0. Therefore, this product for the third surface is again equal to 0. So that means the third surface will not contribute to the flux. Okay. So that means we have only this, we have to consider only this surface, and we already found it. So it is equal to E times A times cosine 0, and cosine 0 is equal to 1. So therefore the net flux passing through this surface, this Gaussian surface, the whole Gaussian surface is equal to E times A. Okay. So now, so this is the one way. So here we found the flux. And using the Gauss's law, again we can find the electric flux. So the Gauss's law says the electric flux is equal to enclosed charge divided by epsilon 0. So we already found this enclosed charge, which is equal to sigma times A. So here is sigma times A divided by epsilon 0. So that means we found flux using two different equations. So here is the one equation, flux is equal to E times A. And using the Gauss's law, we also found flux is equal to sigma A divided by epsilon 0. So that means E times A equals sigma A divided by epsilon 0, like this. And then what happened, this A cancel with this A, and then we can find the electric field near a conducting plates as E equal charge density divided by epsilon 0. So if you remember in the previous slide, we found electric field near a charge sheet, large sheet of charge. In that case, we had a denominator 2. We had a 2 in the denominator, but in this case, we don't have any number in the denominator because we have just one. We only consider this surface because the contribution from the third surface and the second surface for the flux is equal to 0. So that means finally the electric field near a conducting plate is equal to sigma charge density divided by epsilon 0. So that's very important. And then I told you the electric field inside a conductor is equal to 0, and then why it is equal to 0. So let me explain it. Let me go to the next slide. So here you can see, so let's assume we have a uniform electric field. So here you can see field lines are parallel to each other. So we have a uniform electric field here. So now what I'm going to do, I'm going to place a conductor, uncharged conductor, inside this electric field. So then what happened? So then this is the uncharged conductor. So the uncharged conductor mean the number of positive charges equal to the number of negative charges. So after we put this one inside this electric field, then what happened? Charges will distribute like this. The negative charges come to this side and positive charges come to this side. So it's polarized. And then what happened? But still the net charge is equal to 0. However, this induced charge produce a field within the conductor that exactly cancel the external field. Therefore, electric field inside the conductor becomes 0. So here you can see it. So here is the electric field due to this polarized charge. It's going from positive to negative. So this is the electric field due to this polarized charge. And here is the original electric field, which is this one, and then these two will cancel. Therefore, electric field inside this conductor is equal to 0. So that's why electric field is equal to 0 inside the conductor, because these two fields will cancel. So then finally, so we found the electric field near a conducting plate. So that means you can see this is the parallel plate capacitor. So here you have two plates. Those two plates are parallel to each other, and the electric field between these two large parallel plates is given by this equation. So we already derive it. So electric field between these two plates is equal to charge density divided by epsilon 0. Here's our final result. And also we can define the electric field between these two plates equal to capital V, the potential difference between these two plates divided by distance between these two plates. So E is equal to sigma divided by epsilon 0, O is equal to capital V divided by simple T. And thank you so much for your attention.